So, good morning to everyone. Myself, Dr.G.Revathy, Assistant Professor, Department of Computer Science and Engineering, Erode Sengunthar Engineering College. Right now, I'm going to take the topic on trees, and I'm going to explain about trees, and also I'm going to detail explain about binary search trees, and we will discuss some gate questions regarding binary search tree. Let me share my presentation with you. Tree terminologies. In linear data structures, data is organized in a sequential order, and in nonlinear data structures, data is organized in a randomized order. A tree is a very popular nonlinear data structure used in wide range of applications. There are many other such nonlinear data structures such as graphs also. In linear data structures, we are having linked list, stacks and queues. A tree data structure can be defined as follows. A tree is a nonlinear data structure which organizes data in a hierarchical structure, and this is a recursive definition. The process is going to be continuously repeated from root node to the end of the tree. A tree data structure can also be defined as follows. The tree data structure is a collection of data, that is nodes, which is organized in a hierarchical structure recursively. In tree data structure, every individual data element is called as a node. Node in a tree data structure stores the actual data of the particular element and link to the next element in the hierarchical structure. Let me give a small example for tree data structure. So here I have given, you can see this one, this is an example for tree data structure. In a tree data structure, if we are having n number of nodes, then maximum there will be n minus 1 number of links. Link is nothing but a connectivity between nodes. I will detailedly explain all the three concepts and terminologies in my coming slides. You just see, this is an example for a tree data structure. It consists of around 11 nodes. So there will be 10 edges, or we call it as 10 links. In each node is called it, each element, data element is called as a node. So first thing, as I said, I will explain all the three concepts in detail. So first concept, root. In a tree data structure, the first node is called as a root node. Every tree must have a root node. We can say that the root node is the origin of the tree data structure. In any tree, there must be only one root node. We can never have multiple root nodes in a tree. There can be any number of nodes. It can be 100, 200, 1000, 10,000, any bulk amount of data nodes, but only one root node, or we call it as, that is the starting or this the origin of our tree. Here if you see, the node A is called as the root node because from the node A, these and the trees is formed. The tree under A, this side is called as left children of A, and this side is called as right children. C node is called as the right children of A. Next terminology, edge. In a tree data structure, the connecting link between any two nodes is called as a edge. In tree with n number of nodes, there will be maximum of n minus 1 number of edges. So in the starting slide itself, I have explained you, if there are n nodes in a tree, the links or the edges will be n minus 1 node, because the root node, there will be no connectivity from the root, there will be no connectivity to the root node, there will be connectivity only from the root node. So this is called as a edge. Edge is nothing but a connecting link between nodes. So for a simple example, I have given this as an edge. So this is also an edge. This is also an edge. Everything, the thing which is going to connect two nodes is called as an edge. Next one, parent. In a tree data structure, the node which is predecessor of any node is called as a parent node. In simple nodes, the node which has branched from it to other node is called as a parent node. Parent node can also be defined as the node with children. If you see, A has connectivity to B and C. So A is a parent node. Similarly, B has connectivity to D, E and F. So B is a parent node. Similarly, C has connectivity to G and H. So C is a parent node. But if you see, D does not have any connectivities, F does not have any connectivities, I, J, K, H similarly. So these are not parent nodes. Child. In a tree data structure, the node which is descendant of any node is called as child node. In simple words, the node which has a link from its parent node is called as a child node. In a tree, any parent node can have any number of child nodes. In a tree, all the nodes except root are called as a child nodes. Okay. So example, see if you have A here, B, I said A is a parent. So definitely the child of A is B and C. Similarly, I said B is a parent. Therefore, D, E, F is a child of B. Similarly, G and H are child of C. I and J are children of E. And K is the child of G. Okay. Siblings. In a tree data structure, nodes which belongs to same parent are called as siblings. In simple words, the node with the same parent are called as sibling nodes. So if A is a parent and the children of A is B and C, so automatically B and C are siblings. Similarly, D, E, F are children of B, so D, E, F are siblings. G and H are children of C, therefore G and H are siblings. I and J are children of E, therefore I and J are siblings. Leaf node. In a tree data structure, the node which does not have any child is called as a leaf node. In simple words, the leaf node does not have any child, or leaf node has no child. In a tree data structure, the leaf nodes are also called as external nodes. External node is also a node with no child. In a tree, leaf node is also called as a terminal node. Okay, so leaf node, external node, terminal nodes, everything the common meaning that will not have any child, or with up to that the tree is completed. So if you see, D is a leaf node, I is a leaf node, J is a leaf node, F is a leaf node, K is a leaf node, and H is a leaf node. That is, they do not have child after them. Internal nodes. In a tree data structure, the node which has at least one child is called as internal node. In simplest words, an internal node is a node with at least one child. In a tree data structure, nodes other than leaf node are called as root node. The root node is also said to be an internal node. If the tree has more than one node, internal nodes are also called as non-terminal nodes. Leaf node is called as terminal nodes, whereas internal nodes are called as non-terminal nodes. The nodes which have a child are called as internal nodes. The nodes which does not have a child are called as external nodes. Degree. In a tree data structure, the total number of children of a node is called as degree of that node. In simplest word, the degree of a node is the total number of children it has. The highest degree of a node among all the nodes in a tree is called as degree of a tree. So when you see the degree of B, the highest children is D, E, F. So the degree is 3. If you consider for A, it has 2 children, B and C. So the degree is 2. If you see for K, no children, degree is 0. Level. In a tree data structure, the root node is said to be at level 0 and the children of root node are at level 1. And the children of nodes of level 1 will be at level 2 and so on. In simple words, in a tree, each step from top to bottom is called as levels. And the levels starts at 0 and increments at each step. So at root node, the level is 0. The children of root node comes under category level 1. Again, the children of that nodes will come under the level 2 and the steps continuously repeats until the n number of levels. Height. In a tree data structure, the total number of edges from leaf node to a particular node in the longest path is called as a height of that node. In a tree, height of the root node is said to be height of the tree. In a tree, height of all leaf nodes is 0. So, whereas degree started from the root node and end at the leaf node, whereas height starts at the leaf node and it will end at the root node. So, at the level of leaf node, the height starts with 1. The before level, the height 1. And at that before level, height 2. And finally, at the root node is the nth height of a particular tree. Depth. In a tree data structure, the total number of edges from root node to a particular node is called as depth of that node. In the tree, the total number of edges from root node to a leaf node is the longest path, said to be the depth of a tree. In simple words, the highest depth of any leaf node in a tree is said to be depth of that tree. The depth of the root node is 0. So here the depth starts with 0. The next level depth is 1. The next level depth is 2. And it continuously repeats until the nth level. Path. In a tree data structure, the sequence of nodes and edges from one node to another node is called as path between the two nodes. Length of the path is the total number of nodes in that path. For an example, if I want to travel to J, the path will be A to B, B to E, E to J. Suppose if I want to travel to K, A to C, C to G, G to K. Suppose if I want to travel to H, A to C, C to H. Subtree. In a tree data structure, each child from a node forms a subtree recursively. Every child node will form a subtree on its parent node. So if you have, this is a particular subtree, this is a particular subtree, this is a particular subtree. From a child, if we form any tree, that tree is called as a subtree to the main parent tree. So tree representations. A tree data structure can be represented in following two methods. The methods are list representation, left child, right child sibling representations. So we are coming to our topic, binary tree data structure. In a normal tree, every node can have any number of children. A binary tree is a special type of tree data structure in which every node can have only maximum of 2 children. One is known as left child and other is known as right child. A tree in which every node can have maximum of 2 children is called as a binary tree. In a binary tree, every node can have either 0 children, 1 child or 2 children, but not more than 2 children. So this is a simple example for binary tree. So there are 3 types of binary trees. First one, strictly binary tree. Second one, completely binary tree. Third one, extended binary tree. Strictly binary tree. In a binary tree, every node can have maximum of 2 children, but in strictly binary tree, every node must have at least 2 children or 0 children. That is, 1 child is not allowed in strictly binary tree. That means every internal node must have exactly 2 children or 0 child. A strictly binary tree can be defined as follows. A binary tree in which every node has either 2 or 0 number of children is called as strictly binary tree. Strictly binary tree is also called as full binary tree or proper binary tree or 2 tree. So this is an example. Either it will have 0 child or it will have 2 child. There is no case of 1 children. Next category, complete binary tree. In a binary tree, every node can have a maximum of 2 children. But in strictly binary tree, every node should have exactly 2 children or none. And in complete binary tree, all the nodes must have exactly 2 children, and at every level of complete binary tree, there must be 2 level number of nodes. For example, at level 2, there must be 2 power 2, 4 nodes. And at level 3, there must be 2 cube, 8 nodes. A binary tree in which every internal node has exactly 2 children and all leaf nodes are at same level is called as complete binary tree. A complete binary tree is also known as perfect binary tree. So this is an example. Every node is having 2 children. Extended binary tree. A binary tree can be converted into fully binary tree by adding dummy nodes to the existing nodes wherever required. The full binary tree obtained by adding dummy nodes to a binary tree is called as extended binary tree. So this was the original tree, and we added some dummy nodes which are indicated in pink color, which indicates that this node comes under the category of extended binary trees. Binary tree representations. A binary tree data structure is represented using 2 methods. Those methods are array representation and linked list representation. This is an example for an binary tree. It consists of 0 child, 0 children, 1 child and 2 children. So first category, array representation of binary tree. In array representation of binary tree, we use one-dimensional array, 1D array, to represent a binary tree. Consider the above example. This is the above example. Now, for this example, we are going to make the array representation. To represent a binary tree of depth n using array representation, we need one-dimensional array with maximum size of 2n plus 1. So this is the simple representation of this tree. So A followed by its left child B, followed by its right child C. Similarly, B followed by its left child D, right child F. Similarly, C followed by its left child G, right child H. Similarly, D followed by its left child I, right child J. Next category, F does not have any children, either left child or right child, so we will put nils. Similarly, G does not have left child, it has only right child, so we will put nil for left child and in right child K. Similarly, for H, no children, so we will put nil. Next category, linked list representation of binary tree. First we saw array representation of binary tree. Now we will see linked list representation of binary tree. We use a doubly linked list to represent a binary tree. A doubly linked node consists of three fields. First field for storing left child address, second for storing actual data, and third for storing the right child address. In a linked list representation, a node has the following structure. The above example of binary tree represented using linked list. See, this is the data, left child address, right child address. It is a doubly linked list. So we are having the tree. For this tree, we are going to represent using linked list. So A has two children, B, C, A. So this is having left child address points to B. This is having right child address point to C. Similarly, everything. If I don't have left child and right child, I'll put null in that place. So B's children D, F. C's children G, H. So these children I, J. I and J does not have any child, so I'll put null. F does not have any child, I'll put null. G does not have any child, I'll put null. And G has a right child, I'll put K. K does not have any child, so null. H does not have any child, null. Next one, binary tree traversals. When we want to display a binary tree, we need to follow some order in which all the nodes of that binary tree must be displayed. In any binary tree, displaying orders of nodes depends on the traverse method. Displaying or visiting order of nodes in a binary tree is called a binary tree traversals. There are three types of binary tree traversals: in-order traversals, pre-order traversals, post-order traversals. So this is our binary tree. Example for our binary. In-order traversal is nothing but we will visit the left child, root, right child. In in-order traversal, the root node is visited between the left child and the right child. In this traversal, the left child node is visited first, then the root node is visited, and later we go for the right child node. This order traversal is applicable for every root node of all the subtrees in the tree. This is performed recursively for all the nodes in the tree. In the above example of binary tree, we will try to visit the left child of root A, but A has the left child B. B is the root node of the left subtree. So if we try to visit B, B's left child is D, and again D's left child is I. So we try to visit its left child I, and it goes to its leftmost child. So first we visit I, then we go for root node D, then we visit the right child J. With this we have completed the left part. Then we visit B, then we will visit B's right child F. With this we have completed the left part of root node A. Then visit root node A. With this we have completed left and root parts of node A. Then we go to the right part of node A. In right of A, again there is a subtree with root C. So we go for left child of C. Again it's a subtree with root G. But G does not have left part. So we visit G, and then we visit right K. We have part of node. It this we have D, J, B, K, order follow left child, follow right child. Pre-traversal, the root node is visited before the left child and right child nodes. In this traversal, a root node is visited first, then its left child, and later its right child. The pre-order traversal is applicable for every node of all subtrees in the tree. In the above example of binary tree, first we visit root node A, then visits its left child B, which is root of D and F. So we visit B's left child D, and again D is a root for I and J. So we visit D's left child I, which is the leftmost child. So next we go for visiting D's right child J. With this, we have completed root, left and right parts of D and root, left parts of node B. Now B visits its right child F. With this, we have completed root and left parts of node A. So we go for A's right child C, which is a root node for G and H. After visiting C, we go for its left child G, which is root node for K. So we visit left of G, but it does not have the left child. So we go for G's right child K. With this, we have completed the node C's root and left part. Next, we visit C's right child H, which is the rightmost child in the tree. So we stop the process. This means we have visited in the order of A, B, D, I, J, F, C, G, K, H using pre-order traversal. Post-order traversal. So it is in the mode of left child, right child, root. In post-order traversal, the root node is visited after the left child and right child. In this traversal, left child node is visited first, then its right child and then the root node. This is recursively performed until rightmost node is visited. Here we visit in the order of I, J, D, F, B, K, G, H, C, A using post-order traversal. Next one, binary search tree. So binary search tree comes under the category of binary tree. This is in a binary tree, every node can have maximum of 2 children, but there is no need to maintain the order of nodes based on their values. In a binary tree, the elements are arranged in the order they arrive at the tree from top to bottom and left to right. A binary tree has the following complexities: search operation O of n, insertion operation O of 1, deletion operation O of n. To enhance the performance of binary tree, we use a special type of binary tree known as binary search tree. Binary search tree mainly focus on the search operation of a binary tree. Binary search tree can be defined as follows. A binary search tree is a binary tree in which every node contains only smaller values in its left subtree and only larger values in its right subtree. In a binary search tree, all the nodes in the left subtree of any nodes contains smaller values and all the nodes in the right subtree of any nodes contain larger values as shown in the following figure. And this is the figure node, root node with value k. Left side will be all the values less than k and right side will be all the values greater than k. So this is a simple example of binary search tree. Our root node is 25. So all the left elements will be less than 25 and all the right child tree, all the right subtree will be greater than 25. So every time you remember, the left child will be lesser than the root node, right side will be greater than the root node. Operations on a binary search tree. Every binary search tree is a binary tree, but every binary tree does not need to be a binary search tree. The vice versa is not true. The following operations are performed on a binary search tree: search operation, insertion operation, deletion operation. Search operation. In a binary search tree, the search complexities are performed with O of log n time complexity. The search operation is performed as follows. Step 1. Read the search element from the user. Step 2. Compare the search element with the value of root node. Step 3. If both are matched, then display given node is found and the function is terminated. Step 4. If both are not matched, then check whether the searching element is a smaller element or larger element than the root node. Step 5. If search element is smaller, then continue the search process in left subtree. Step 6. If search element is larger, then continue the search process in the right subtree. Step 7. Repeat the same until we find the exact element or until the search element is compared with the leaf node. Step 8. If we reach to the node having the values equal to the search value, then display element is found and terminate the function. Step 9. If we reach to the leaf node and it is not matched with the search element, then display element is not found and terminate the function. Insertion operation in a binary search tree. In a binary search tree, the insertion operation is performed with the O of log n time complexity. In binary search tree, new node is always inserted as a leaf node only. The insertion is performed as follows. Step 1. Create a new node with given value and set its left and right to null. Step 2. Check whether a tree is empty. Step 3. If tree is empty, then set root to new node. Step 4. If tree is not empty, then check whether the value of new node is smaller or larger than the node. Step 5. If new node is smaller than or equal to the node, then move to its left child. If new node is larger, then the node move to the right child. Step 6. Repeat the above steps until we reach the leaf node. Step 7. After reaching the leaf node, insert the new node as left child if the node is smaller and right child if the node is larger. Deletion operation in a binary search tree. In a binary search tree, the deletion operation is performed with O of log n time complexity. Deleting a node from binary search tree includes three cases. Deleting the leaf node, that is a node with no child, deleting a node with one child, deleting a node with two child. First case, deleting a leaf node. We used to perform the following steps to delete a leaf node from a binary search tree. Step 1. Find the node to be deleted using search operation. Step 2. Delete the node using free option. Case 2. Deleting a node with one child. We use the following steps to delete a node with one child from binary search tree. Step 1. Find the node to be deleted using search operation. Step 2. If it has only one child, then create a link between its parent and child node. Step 3. Delete the node using free function and terminate the function. Case 3. Deleting a node with two children. We use the following step to delete a node with two children from a binary search tree. Step 1. Find the node to be deleted using search operation. Step 2. If it has two children, then find the largest node in the left subtree or smallest node in the right subtree. Swap both the deleting node and node which is found in the above step. Step 4. Then check whether deleting node comes in case 1 or case 2 or else go to step 2 again. Step 5. If it comes to case 1, then delete using case 1 logic. If it comes in the case 2, then delete using case 2 logic. Repeat the same process until node is deleted from the tree. Okay. So we will construct this tree and I'll show you in parallelization. We'll open it in we'll open it. Now going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same order. You can see how it is to be inserted. Now, going to insert the elements in the same or So we are going to construct search first all the elements. The element order 12, 4, 20, 8, 7, 30. Okay. What I'm going to insert 10 inserted. The next 12. 12 is greater than 10. So it will be inserted as a right. Next 5 is here smaller than 10. So inserted as a left. Next 4. 4 is less than, again less than 5. So as left to 5. Followed by 20, 20 greater 10 than 12 will be inserted as right child to 12. Next degree, so 8 is less than 10. So when it comes to 5, it is 5. So inserted as next 7. When it comes less than, it is greater less than 8, inserted left 8. Next 15, than 10, greater than 12, less than 20, inserted as child 20. Next one, greater than 10, greater than 12, less than 10, less than 15, so we insert as left to. So this loading. So in the mean, will so question is this. So this question asked computer science in the year 2011. Question is this one. They are giving a set of we'll insert in this order. We'll choose 10 till 5. First set. I'm going to insert 10. Next one. Greater again right child 20 less greater, so right child will go 7, lesser, greater, lesser, so left subtract, followed by 15, great, lesser, so it will left. Now 13, greater, greater, lesser, lesser, so left side. So this is what we saw. The tree is inserted as we saw in our presentation. The same tree structure visualize. So show some examples such as deleting the node just not inside. So see, now I'm going to delete 4 because it doesn't have any child, just 4. See, delete. There will be no issues. First it will search for element 4. It will find it does not have any child, automatically deleted. Now you will see 8 has 1, 7. So how going to delete? So 8. Now delete option. So 10 lesser element 5 greater than 8. It has found 8. So swap 1, 7 and it will be deleted. So 2 child. Example, I'll insert some 23. 23 greater than 10, greater than 12, greater than 20. So it will be formed as a right child to 20. Now 20 as well as I'll delete 20. What is performing? Greater again element. Now 15 will be placed and 20 will be deleted. Okay. To find 12. First it will take greater option and 5. Suppose I want to find 7. So let us see 6. What's happening? No, the element is not present. In display, not. Suppose I want to search 7. We'll do it. 5, 7. Element is formed 7. Okay. So as I said, we'll do some conditions. We are given with set of n distinct elements and an unlabeled binary tree with n nodes. In how many ways we can populate the tree with a given set so that it becomes a binary tree? The question is, we are having n distinct elements and an unlabeled binary tree. How many ways we can populate the tree? Answers are A0, B1, C n factorial, that is n element factorial, D 1 by n plus 1 into 2n C of n. So the answer, there is only one way. The minimum value has to go to leftmost node and maximum value has to rightmost node. Recursively, we are going to do the same process only. Minimum in the left side, maximum in the right side. So answer is B. Now I will highlight B. Answer is B. Next question. The following this question is again a GET question which is asked in the year 2004. The question is, the following numbers are inserted into an empty binary search tree in the given order: 10, 1, 3, 5, 15, 12, 16. What is the height of binary search tree? The height is the maximum distance of leaf node from the root node. So if you want to perform this, we'll take our visualization and what we are going to do is we'll delete all the nodes so that we'll get a new tree. I'll make the animation speed faster. We have to insert the first 10, insert 10, next 1, insert 1, next insert 3, next insert 5, next insert 12, next, sorry, I have wrongly inserted, I should not insert, next 15, insert 15, then insert 12, I think you can go a bit slow, insert 12, next insert 16. So a complete binary search tree is formed. We have inserted in the order they have given. So the question is now, what is the height of the binary search tree? The height is the maximum distance of a leaf node from its root. Okay. So we will predict. This is the maximum node, I suppose. We'll go with the answer 3. And The tree structure formed. Can we check with this tree structure? The same tree node structure that we formed. The same tree node structure. The height is 1, 2, and 3. So as we predicted, the height is 3. That is, this is the required answer. Okay. So as of this, I have discussed with you the basic terminologies of trees, the basic concept of a binary tree, the basic concept of a binary search tree, the algorithm for insertion and deletion and searching operation, the visualized representations, and the gate presentation. So next video, we will meet with different kind of trees, graph algorithms, and also with some linear data structures also. Again, thank you. This is Dr.G.Revathy, Department of Computer Science and Engineering, Erode Sengunthar Engineering College, Autonomous. Thank you. Visit again.